Welcome back. In this video we are going to look at something called the linearization theorem. And the linearization theorem allows us to look at nonlinear equations and begin to think about them as if they were their linear counterparts. So many real-world systems of differential equations are nonlinear. This means they do not allow us to use the eigenvalue-eigenvector approach to finding solutions. As a matter of fact, many of these nonlinear systems are even unsolvable. But not all is lost, because a nonlinear system tends to have more than one equilibrium point, and one of them is not always 0, 0, as is the case for a linear system. These equilibrium points, though, tend to have similar classifications. So sink, source, saddle, spiral sink, spiral source, and center. They look very similar a lot of times. And the ability to classify them as one of these will allow us to understand how the trajectory of an initial condition may take it towards certain equilibrium points and repel it from others. So before we get into this theorem, let's go ahead and consider a nonlinear system. This is a variation of the Lotka-Volterra model for competing species. And for fun, let's just say that X represents the number of zombies and Y represents the number of werewolves within a particular region. And the question that we should ask ourselves first of all is, what do we notice about their interaction with and without the presence of the other? So to kind of make sense of this, this is called a competitive model. And I picked two species, or two imaginary species, that are competitive in the sense that they both seem to go after human flesh, but they do not eat each other. However, we could probably argue that the overabundance of one could lead to the decimation of the other, just by virtue of the fact that perhaps one is consuming the source of food for both of them. So first of all, one thing that we should notice is that if there's 0 of either of the two species, then that's going to result in, first of all, complete extinction of one of the species, right? So if x were to equal 0, then we would see that dx dt would reduce to 0, which makes sense, because if there are no zombies, we would expect none to be recreated. And similarly, if x is 0, that means dy dt, the second equation, the second term goes away, and you end up with 3y times 1 minus y over 3. Now this system here is one that has this equation here is one that has an equilibrium point at y equals 0 and at y equals 3. And so at y equals 0 and y equals 3, if we were to look at this over time, we would see kind of this logistic curve, and the population would approach the carrying capacity. So that would be without the presence of werewolves. Of course, we wouldn't expect them to grow indefinitely, because they also need to have a food source, and they don't want to dupe themselves. So now when y is equal to 0, and there are 0 werewolves, then dx dt becomes logistic. We see that the second term here goes away, and we're left with 2x times 1 minus x over 2. And so that's again going to be a logistic growth, but in this case, rather than to have 0 and 3 as equilibrium points, unfortunately you can't quite have as many werewolves. They're a little bit more, have a higher appetite and probably consume more per werewolf. But of course, if y equals 0, we see that the second equation clears out, and we're left with dy dt equals 0, which makes sense. If there are no werewolves, then there will not be any. There will not become any. And then we wanted to ask how these two interacted. Well, first of all, we see that in the absence of the other, they both do just fine. But in the presence of one another, we see that we have this subtraction term here and here. And that subtraction term, or the size of it, is based on the sizes of the two populations. So if x is really large and y is really large, then the product is going to be really large. And if the product is really large, then that's going to subtract or create a big negative contribution to dx dt. So it's the interaction, the fact that if these two beasts are in too close of proximity, their interaction actually leads to destruction of both species. In the case of the werewolves, the presence of the zombie is more detrimental than for the zombies in the presence of the werewolves, because of this factor of 2 here. So it's doubly detrimental to, the interaction is doubly detrimental to the werewolves as it is to the zombies. So this is a competing species. We see that a high interaction rate actually is bad for both of them. And that you can see this where you have predator-predator situations or prey-prey situations, as opposed to predator, one being the predator and the other being the prey. So interesting model here, one that we want to better understand. And of course, this is in realistic terms used to model interactions between any two competing species in an environment. So if we consider the phase plane of this nonlinear system, and recall it's nonlinear because of the interaction terms here, this is what makes it nonlinear, is these two terms here. You have the product of dependent variables. Although it's not like saying x squared, it's two dependent variables multiplied together. So it is as if we're kind of squaring a dependent variable in a way. So the phase plane, as we look at this, we notice that it's pretty erratic. It's kind of hard to predict. It doesn't look like our linear systems. We see that over in the first quadrant, it looks like some solutions maybe, kind of curve in this way. Looks like here they come in this way, here they come straight down. But then over in this quadrant, it gets really crazy. It's almost like there's some sort of looping structure here. And out here, the solutions seem to veer out that way and maybe veer downwards. And here again, they kind of loop. So it's a very chaotic looking system. And that's troubling because in order for us to have a good sense of what's going on, we need some sort of tools with which we could better understand why what's happening is happening. So let's also take this side road and say, let's look at the equilibrium points of the system and see if somehow that allows us to see anything. Before we get at that though, let's go ahead and pull up this phase plane and play around with it a little bit. So recall this is our grapher app, and I just have the two differential equations input in here, dx dt equals 2x times quantity 1 minus x over 2 minus xy, and dy dt similar. Independent variable is t. And here we're just looking at from time 0 to time 10. You can always change that if you want, and we can move the initial condition around the phase plane. Now the other thing that I want to ensure is that I'm going to choose RK4 system from here. That's the most precise of the methods available, and change the step size to 0.01. Otherwise the trajectories look kind of square. So you'll see what I mean. If I change that to 1, for instance, you're going to see something that's remarkably, well, in this case, we don't see anything at all. So let's try 0.1 and see if that will give us a better representation. So here these trajectories just kind of look very line-ish. And by setting the step size to be smaller increments, we'll have, instead of having 1 line here, we'll have 10 lines if we make the step size 0.01, so it looks more smooth. So you can see that depending on where I click the initial condition, in here we kind of saw these loops, and you can look at, so here we have the x-axis and here we have the y-axis, and then this of course sketches, here we have y versus time on the right, and you can see what y does for that initial condition. Y kind of hops up from a small positive value, hops way up here, and then the y value starts to descend back down, and it looks like it flattens out. It goes to some sort of point here and then just sort of stops. And it seems like all these initial conditions seem to do that. They come to this point and then just sort of flatten out. Already I'm beginning to think that there's an equilibrium point right there because I see that the population stops growing. And the same thing for the x population. We see that initially x is negative and x becomes more negative. It moves to the left, so this drops down until about here, at which point the x values start to approach 0 again. And so it looks like 0 is an equilibrium point. Here, if I kind of cursor over that, it looks like right around y equals 3 and x equals 0. So this looks like it might be the point around 0, 3, which looking at the coordinates here, yeah, it looks like x is about 0 and y is about 3. Now over here, depending on where I click, here it looks like certain trajectories are going straight to this point here, which looks like y is descending to 0, and x looks like it is hitting about 2 or so, right around 2 as time approaches infinity. But then as I move this initial condition, watch what happens. After a certain point, wow, look at that trajectory. Now that trajectory goes to that same thing that we were calling the equilibrium point. The x value over time descends to 0. The y value seems to now ascend to 3. And then things get even chaotic in here. They seem to be going to that same equilibrium point right there, 2, 0. And out here, just a very different behavior. So we're going to do two things. One, we're going to try to analyze the equilibrium points and understand whether they attract or repel solutions. And then in the next lesson after this, we'll get into how do we understand or break up this phase plane into more manageable chunks. So let's go back and do some investigation.